Hello everyone and welcome back to this lecture series on powder metallurgy. This is the second class today of this particular course. In the first one we have seen the introduction of the powder metallurgy process, and while talking about the powder metallurgy process what we have seen is that the starting material is the powder, okay, and then you take the powder, process it through a certain number of steps to finally get to the product which you want. Okay. So, since the powder has a lot of influence on this process, you need to first see how the powder is fabricated, because the fabrication process will actually influence what is the type of powder in terms of many of its characteristics and properties. Okay. So, today in this class we are going to see how powders are fabricated. We will be mostly dealing with metal powders here. So, we will see how metal powders are processed and manufactured. Okay. So, talking about powder fabrication, there are several fabrication methods which are available, and as I said, the fabrication method will actually decide the characteristics of the powder. So, that is why it is necessary for us to actually understand each of these fabrication processes and see how they are done and what kind of powders are obtained when you use a particular type of fabrication process. So, one thing that we also know is that any material can be made into powder, and the method selected for fabricating depends on the specific material properties that you want, right. So, you can start with any material that you want, and then you can make powders out of it, and finally, you process the powders and get the desired product that you wanted. Okay. So, as far as the powder fabrication methods of powder fabrication processes are concerned, there are primarily 4 types of processing methods which are categorized in these 4 different categories. As you can see over here, these are mechanical, electrolytic, chemical and atomization. Okay. So, we are going to take each of these individually one by one and talk about them in more detail, and you will also see in some of these categories there are several other processes, different types of processes that can be grouped into one particular type of fabrication method. Okay. So, all this we are going to discuss in detail in today's class. So, let us start with the first one which is the mechanical method of powder fabrication. So, mechanical fabrication or mechanical method of fabrication means you apply a mechanical force, and with the help of that mechanical force you make small fragments from a material and make a powder out of it, right. So, this mechanical force can be applied by different means and ways. As far as powder processing is concerned, there are primarily 4 methods by which you can apply this mechanical force, and these are as follows: impaction, attritioning, shearing and compression. Okay. So, primarily these are 4 types of mechanical actions which are used to make metal powders. Impaction is nothing but rapid instantaneous delivery of blows resulting in cracking and fragmentation of the material. So, mechanical fabrication is actually a top down approach, as we call it. Which means you start with a a bigger size material and break it down to smaller and smaller fragments till you get the powder, right. So, for example, in case of impaction, you apply these rapid blows or rapid or you impact the material rapidly, so that it fragments, and you keep on fragmenting it into smaller and smaller pieces, and finally, you obtain the powder. Okay. Similarly, in attritioning, instead of impacting, you use rubbing action. Okay. So, here the size reduction is by rubbing action. So, you apply something onto a bigger chunk of material, you apply this mechanical force with the help of, for example, some kind of impellers inside a container, and subject this material to high amount of deformation with the help of those impellers. And when the material rub against these impellers or against each other, they fragment into smaller pieces. That is what is called attritioning. And then you can also subject the material to shearing, which is a cleavage type of fracture by cutting. And in this case, the powders formed are coarse and not often used in powder metallurgy. The powder which is made by shearing, since it is like a cutting kind of mechanism, these are quite coarse powder, and that is why they may not be very useful in powder metallurgy processing, because in powder metallurgy processing what you need is a what we call as a good packing characteristics, so that the powder particles can pack together and give you a compact which can be easily shaped and processed. Okay. So, if these particles are very coarse or very rough, then the packing characteristics are not very good. Then comes compression, which is nothing but breaking down a sufficiently brittle material into coarse powder by compressive forces. So, here as the name itself suggests, you apply compressive forces on a material and break it down to smaller and smaller fragments. Okay. And while you want to achieve a particular type of powder, often these methods are combined, so that you can get a particular type of powder, or you can achieve certain properties in the powder. And the powders which are fabricated by mechanical methods are typically irregular in shape. Okay. So, that is the typical characteristics of powders which are made by this mechanical fabrication route. Now, if you go into details as to how this each of these method works, for example, if you talk about the impaction, the first type of mechanical method that we talked about, this, as I said, you have to impact the material rapidly with some force, so that it breaks down. Okay. For example, in case of milling, you can impact the starting material which is much larger or much coarser in size with hard balls or hard metal balls or hard balls made of any other materials which are very hard. So, with the help of those balls, you can impact the material and you can fragment it. So, in order to do that, you actually need a container in which you can fill these balls and the material together. Okay. And then you apply some kind of mechanical action, for example, rotation or some other movement, so that these balls can collide with the material and fragment it. So, in case of jar mill or ball mill, for example, you use a jar as a container, which is also known as a vial, and fill this container with the ball and material in a certain weight ratio. Okay. So, for example, in case of ball mill, as you could see in this image over here, this is the schematic of the container, in which you have these balls, and here you also will have the material along with that, right. Let us say this is the material that you have, which you want to fragment down into powder. Okay. So, if you rotate this container now at a given speed, at a given RPM, then these balls will go up, and then as they reach here, they will fall down again and crush against the powder or the material that you have, and crush it into smaller fragments or into powders. Okay. So, as I said, balls will collide continuously with the material and crush it into powder. So, one thing that you need to make sure here is that the rotation speed which is used should be optimum, right, because if the speed is not fast enough to carry the balls to the top from where they fall onto the bed of material, then that whole purpose of the balls going up and then falling down on the material will not be served, okay, if it is too slow, right. So, it should be fast enough so that the balls can reach all the way to the top, and from there they can fall down on the bed of material. Similarly, it should not be too slow also on the other hand, because if the speed is too slow, that will result in balls rolling back and not really going to the top and falling on the material, right. And if you are too fast on the other extreme, then it will result in centrifugal force, and the balls will simply stick to the wall of the container because of the centrifugal force, right. So, it should not be too fast, and it also should not be too slow. It should be just fast enough, so that the balls can be carried to the top, and from there they should fall down again instead of sticking to the wall of the container, right. So, that is how, as I said, it should not be too fast, otherwise it will lead to centrifugal force. If it is too slow, then the ball themselves will not reach to the top, and they will simply roll down. Okay. So, you need to kind of optimize this rotation speed when you use this ball milling process. So, this is one type of mechanical action which can be used to make metal powders, and as far as the process parameters go, you can see here the impact stress is given by this particular equation over here. Okay. The impact stress sigma is equal to this, wherein E is the elastic modulus of the material which is being processed, R is the crack tip radius, because when the balls impact the material it is going to crack. So, R is that crack tip radius, and D is the particle size, which you achieve by breaking this material into smaller fragments. Okay. So, from here one thing that you can notice is as D reduces, sigma goes up, right. So, that means if you fragment it more and more and make the particle size smaller, then the stress required to break it down further will also increase significantly, and that is why prolonged milling is less productive, since the stress requirement will significantly increase as the particle size goes down. and the energy required in this process is given by this particular equation, and this depends on what is the final size d f that you need. The energy needed will be dependent on that. Okay. So, in this particular equation G is a constant and A is a constant which is in between 1 and 2. Okay. And this again varies with relative change in particle size, and thus the milling time will depend on the available powder, the size change, the milling media size and the rotation speed. Milling media size is nothing but the size of the balls that you use. So, milling media means in this case, in case of ball milling are those balls which are used to impact the material so that it can be fragmented. Okay. So, how this energy input will be, that also depends on the size of the ball, apart from the other parameters like the rotation speed, milling time and so on. And in case of this ball milling process, at times if needed fluid and protective atmosphere can be also used to aid the grinding process and also to prevent oxidation. So, if you have a metal which is prone to oxidation, you should be also able to use a protective atmosphere so that the oxidation can be prevented. Okay. And sometime a fluid or a liquid can also be used to aid the grinding process. So, in that case what we call that process as wet milling, where you have a liquid medium aiding the grinding process or this ball milling process. Okay. So, fluid or liquid can also be used to make it more effective. And the powder generated is work hardened because it is continuously impacted by those hard balls, and these powders are irregular in shape and they exhibit pore flow and packing characteristics. Okay. The other issue with this process is the contamination that comes from the jars and the balls, because this jar and the balls are made of a different material most of the time, because these balls and the jar also have to be very hard. So, more often than not they are made out of a different material which are very hard. So, there are chances that some contamination may come from the jar and from the ball into the material which is being processed. And the other limitation is that this process is not good for ductile metals, because what happens in case of ductile metals is that when you impact it with the balls, instead of fragmenting, because of their ductility they will weld together, okay, which is known as the cold welding. So, instead of reducing in size, they will grow in size by welding together. So, that is why for ductile metal this process is not that effective because of this problem of cold welding. Okay. But one of the advantages that you have in this process of ball milling is that you can combine different material and you can make an alloy, okay, or you can also make composites. If you are not making alloy and you simply want to combine 2 or 3 different materials, then you can combine them into a composite material. Of course, in that case you will have to use a high energy ball mill, so that the energy input is high, because in that case you are actually trying to add a second material into the first material, into the main material that you have, So, your energy input should be higher in that case. And in order to do that, in order to have this high energy input, you will have to use hard balls like tungsten carbide balls, and also containers which are made of the same material. And apart from that, other hard materials like the ceramic materials such as alumina and zirconia can also be used as the milling media. And in this case, as I would have mentioned before also, a certain ball to powder weight ratio has to be maintained. For example, a 20:1 weight ratio, that means your weight of the balls is 20 times more than the material which is being used. So, that kind of ball to powder ratio, which is in short known as BPR, is used. So, that would depend on what kind of material you have. This BPR may vary from material to material. And this process of alloying or mechanical alloying, as it is called, because you are using mechanical forces here to make the alloy. This mechanical alloying process was originally developed for making a particular type of material known as oxide dispersion strengthened alloys, in which you add fine particles and disperse them in a material to make it stronger. Okay. So, originally, although it was developed for these ODS alloys, but now this process can also be used to make other type of materials, including different types of alloys. Grinding time or milling time is a parameters as I had mentioned before, and that time actually depends on certain other parameters which are given here in this equation, wherein D is the size of the grinding media, that means the size of the balls or the diameter of the balls. N is the rotation speed which is being used, and C is an empirical constant which depends on the specific process and the level of homogeneity which is desired. And in this case of in this particular process, the powder particles which are obtained are generally irregular in shape, which you can see from this scanning electron microscope image. The powder particles are irregular. Okay. And this is the process of attritioning. If you remember, we had talked about that also before. That is the another method of applying the mechanical force. So, here what you do, you use these impellers, as you can see over here, and with the help of this impeller you actually break down this material into powder. Okay. So, here there are different parts in this attrition mill, as you can see from this figure. Here you have this shaft over here, and if you look at inside this jar which contains the material, in this shaft you have these impellers attached to it at different angles, right. And then you rotate this shaft. So, these impellers will also rotate and they will impact or they will rub against this material and break it down into smaller fragments and give rise to a powder material, right. And along with this material, you can also mix hard balls, so that these balls can also be used to impact the material and break them down. And these impellers will actually help them in providing that agitation and the mechanical rotation or the mechanical movement. So, these balls can collide against the material and break it down into powder. So, this is the process of attritioning which is done in this kind of attrition mill, which basically has this container in which you have these mechanical impellers, and you load the balls and the powders again in a particular weight ratio, and then you start rotating this shaft, which will rotate these impellers at high speed inside the jar, and with the help of that impact you can break down the material. Okay. So, this is the process of attritioning, and the other impaction techniques which can be used are as follows: compressive crushing down to 1 millimeter and below using tungsten carbide blades. So, you can use a hard surface like this tungsten carbide blades, can apply compressive force to break down the material. Then there is a process called cold stream method, which is acceleration of coarse powder by a gas jet to collide with a cold target. And in this case you can achieve powders of size around 10 micrometers, and these powders are rounded, but irregular in shape. Application of this cold stream method is for making stainless steel powders for filters and spray powders for coating. And there is a variation for this cold stream method in which is known as self impact attritioning. In case of cold streaming, what is done, these powders are actually made to collide against a cold target, but they can be also made to collide against each other. So, in that case it is known as self impact attritioning, where two streams of same powder are directed at each other with a high velocity, and when they collide at high forces or at high velocity, they fragment each other because of this collision. Okay. So, these are different methods of mechanical fabrication of metal powders, and with that we have come to the end of this particular class. Thank you for your attention.